First, I'd like to thank the organizers for inviting me here, and thank you, ICTS, for hosting such a what seems like a very wonderful program. Uh, it's a win-win for me. I get invited back to my hometown, so I'd come here any day. So my plan for the two lectures is to uh, talk about, I guess the title was what can you do with Markov chains before they mix? But I guess I'll talk about locally stationary measures in the first lecture. And in the second lecture, I will get into some proofs of these things. And when I do that, I'll try to introduce other concepts from Markov chains, which were developed recently. So, and please stop me if you have any questions. We can pace the lecture as it goes. So let me just set up some notation first. So you have a Markov chain. So a Markov chain it has these things. Firstly, you have a finite state space. So the finite state space. Omega, it's just a finite set. And in many of the examples, this will just be the 0, 1 to the n, the Boolean strings. And you have a transition matrix. P, which is, of course, it's a omega cross omega matrix. And it tells you the probability of transitioning from the state X to state Y. And once you have these two things, if let's say this P, the matrix is symmetric, so it gives you like so let's say the chain is time reversible. I'll say what this is. What you'd get equivalently is you have a particular stationary measure. There is a stationary measure. Let me use pi. This is a probability distribution over the states that is invariant under one step of the chain, such that pi p is equal to pi. And so, as I said, we'll only be talking about finite state spaces, and you can think of all our walks as just undirected graphs on the state space, and you have all of them have a stationary measure. But sometimes it'll be kind of convenient for us to sort of take this discrete time chain, where you take one step every time step, to convert it to a continuous time chain. So the continuous time version of this is given by P sub t is the matrix exponential of but one way to think of this simple continuous time version of it is just that you have a clock, a Poisson clock, and it sort of rings every once in a while. And whenever it rings, you take a step. And so for any given time, you can define, it gives you a Markov chain. And that's P sub t. Okay, so this is standard things in Markov chains. So just to give a very important example for us, an important example for us would be global dynamics. So what is global dynamics? So you have, let me, for a distribution pi, so let's just say there is a, fix some probability distribution pi on the hypercube. It's a probability distribution. Now, what is the Glauber dynamics associated to pi? It is the following random walk whose stationary measure is pi. So what is the random walk? You're at some state x. So from state, you're in some state which is like a Boolean string. Okay. What you do is you just pick one of the coordinates at random. Pick I uniformly at random. So you decide out of the n coordinates, you decide to re-randomize some coordinate I. Okay. And then now that you've decided to re-randomize I, you the ith coordinate, you resample the ith coordinate conditioned on the remainings. So, what you do is you resample a bit, let's call it B, from the distribution. You take the pi, your measure, you fix all the bits other than I. If I fix all the bits other than I, then I have some measure for the ith coordinate, and I resample that bit. Let me call it Bi, so that because it's meant to go into the ith space, and then you move to that state. You output, a string where xi is set to b, and then the remaining coordinates are as is. Okay, and you can do this for any distribution over the hypercube. You can define this Markov chain. So to give you a more concrete example, so let's say, for example, let's fix a graph on n vertices. Graph on n vertices. Okay. Now, let's say pi is the uniform distribution over all independent sets of the graph. So uniform distribution over all independent sets. Okay, and of course, you denote sets by binary strings. So this is an element of 0, 1 to the n. So this is a subset of 0, 1 to the n, the set of all independent sets of a graph. Then you follow the same recipe. You get a random walk which is on independent sets of the graph. What is the recipe? Well, let's say you're at state I, which is some independent set. Okay. First, you decide to resample a particular vertex. Let me call the vertex V. Okay, you sample a particular, let me call it, pick. You pick one vertex to re-examine uniformly at random. And then, there are a few cases. Well, basically, if this vertex is already in the independent set, then in some sense, you can keep it. That's still an independent set, or you can delete it. That's also an independent set. So there are two choices, and you're going to pick one uniformly at random. So with probability half, you will output the same independent set I, and with probability half, you output I minus V. Okay, this is exactly just following this recipe for this particular distribution. And the other case, of course, is kind of, suppose the vertex is not in the independent set, then, maybe you could add it to the independent set or maybe not. So if you can't add it to the independent set, so if I union V is not independent, then you just output I, because there's only one choice. So the key is that you've frozen every other vertex and you're just making choices for this particular vertex. And the other is if I union V is an independent set, then, then what that means is you can add this vertex to the independent set. There are two choices. So with probability half, you output I. With probability half, you output I union V. Okay, so this is exactly following this very general recipe for this particular example. Okay, so any questions so far? So this is okay, good. All right, so this is this is an example of a Markov chain, and as I said, every Markov chain, which is nice and time reversible, has a stationary measure, and moreover, Markov chains typically mix. So, right, if you have a Markov chain which is ergodic, or basically a Markov chain where all its there are no one eigenvalues. So let's say if P is ergodic, which is most graphs will be Markov will satisfy this unless you have pick a bipartite graph or something. Then no matter which initial distribution you start with, if I start with any initial distribution for my initial point, and if I run the Markov chain for long enough, then the distribution becomes this converges to the stationary measure. Okay, so this is mixing. So every good question. So yeah, I should. Yeah. Yeah, I should. That's a good question. I should maybe put a bracket here. Yeah. 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 Right. So for this chain, pi will be the stationary measure. And here we start with this pi, so you'll end up with uniformly. So this is, when you look at it, it's pretty impressive, right? It's a very simple operation, and it lets you sample a uniformly random independent set in the graph. Unfortunately, those things don't mix quickly. So, well, we know that pretty much all chains will mix to the stationary measure. They often take in exponential time, right? So mixing can take exponential in n time. Well, I guess when I use this, when I say it this way, what I really mean is we are talking about a random walk on, let's say, 0, 1 to the n. Then mixing could take exponential in n time. Okay, I guess every graph, yeah. So this is problematic because this doesn't give you an efficient algorithm to sample from it. But there's a lot of classical machinery on trying to prove mixing time bounds, where you show that a certain Markov chain, like a global dynamics, for a certain range of parameters, actually mixes in polynomial time or mixes fast. And there's an entire, you could probably spend a semester learning all the various techniques to show fast mixing. Okay, that's good. Except there are very natural chains where mixing does take exponential time and you can't really get around it. And you could ask, well, if mixing does take exponential time, is it of, are such Markov chains of any use? can we use Markov chains where mixing could potentially take exponential time, and what can we do with it? So here's a analogy that I like to draw. So think of the corresponding thing in optimization. Right? In optimization, you're trying to minimize a function, right? And let's say you're minimizing some function over some exponentially large space. And here, well, what do we have? We have the notion of a global minima. And if the function is convex, you can converge to global minima quickly. And otherwise, finding the global minima can be NP hard, right? It would be NP hard to find global minima. But, we have this very standard thing that there are this notion of local minima. And local minima are actually somewhat relatively easy to find. In fact, if you just run gradient descent, it has to go get stuck somewhere. So gradient descent will find local minima or approximate local minima. Okay, and this is very useful, right? In many contexts, just finding the local minima is really, really useful, right? So you could ask, well, what about sampling? So in sampling, you have the same notion. You have a notion of a global minima, which is the true stationary measure. And it's sometimes hard to sample from. Can we define a notion of a local minima, right? Which is easier to sample from. And it should be canonically true that if you just run some very simple canonical Markov chain, it should find an approximate local minima or whatever the notion is. And that is really the definition that I want to state now, which we call locally stationary measure, local stationary measure, locally stationary measure. Okay. So that's where local stationary measure sits. That's the way to think about it. It's an analog of local minima for sampling. Okay, so now we have to define what it means for a measure to be a local minima, a locally stationary measure, right? So here, I guess, let's start with one definition. So I'll change the definition a little quickly soon. So a measure mu, actually, right? Measure mu is locally stationary epsilon locally stationary if, let's say, you could take the total variation distance between the measure nu and one step of the measure nu, and you say this is less than epsilon. Okay. P nu is just one step of taking the measure. Okay, so this is it's just saying that you have a probability distribution, let's say, or independent sets, such that if you take one step of the walk from that distribution, you don't change the distribution much. Yes, it's one definition. Right, the question is, does it imply anything about two steps? We'll come to that, yeah, good point. Any other questions? So let me state another definition. For this another definition, it'll be useful for me to define the Dirichlet form. Okay, so if you have a Markov, so again, phi will be your Markov chain. Okay, So the Dirichlet form, epsilon p, or let's take two functions on the state space. Okay, the Dirichlet form, epsilon p of f comma g, it's a bilinear form, which is basically, you pick a random edge of the chain. So how do you pick a random edge of the chain? You pick a yeah. So you pick a point from the stationary measure, and then you pick y, which is a random edge from there, and then you take the fx difference on that edge multiplied by the difference of g on that edge, and you take its expected value. So I guess for people who have seen this, this is just the Laplacian. This is the Laplacian matrix of the graph of the chain. Okay. Sorry, what was that? Yeah, L is I minus P. Yeah, L is I minus P. So this is just a Laplacian, I minus P, and but this is the form. Okay, why is this form important? Well, oh yes, yes, thanks. Yeah. So this is some notation, I guess. So when I write y x, what I mean is y is one step of the chain from x. Yeah. So why is Dirichlet form important? Well, basically it measures how quickly your chain is converging to the stationary measure. So for example, in the continuous, for continuous time chains, right, you can take the derivative of the difference between your measured PT nu minus the stationary measure. Look at the L2 distance. L2 with respect to pi. Thanks. Yeah. I should just, so this is negative of the basically the Laplacian, the Dirichlet form. So for f, where f of x is I guess I don't need, I could say pt nu of x divided by pi of x. Right. Yeah. Correct. Yeah. Thanks. Yeah. So, okay. So, let me state something more relevant to us. Oh, L2 norm with respect to pi. Oh, okay. What does this mean? So let me state it more simply. So it's okay. Let f be the density of the current measure. So f is the density of the current measure, meaning f is pt nu of x by pi of x. Then the inner product with respect to pi is basically, so let me say, if you have a function g, this is expectation of g square of x, x from pi. So, and okay, let me write something much more cleanly. And this time I'll write it for not the L2 distance, but for our KL divergence. Okay, so you could say, let's just look at the KL divergence. So actually, I should maybe set up some basic notation here. I'll use nu t to be the nu t is the distribution at time t. Okay, and f of t is the density of this distribution. Okay, it's meaning the ratio to the stationary measure. It's better to work with densities uh, because that's what shows up in many of the expressions. Okay, so here's a more relevant fact for us. So if I look at the KL divergence from nu t to pi, and I ask how quickly is the KL divergence dropping? This is exactly equal to the negative of the Dirichlet form. Okay, so the Dirichlet form is basically how quickly is your nu t converging to the stationary measure. And if you can measure it in KL, then it's a Dirichlet form of ft with log ft. Here you can, I said, with 2 norm, you get Dirichlet form of ft with ft. Okay. Okay, so this is the most important equation, I guess, for us. It tells you how quickly the KL divergence is dropping, this quantity. Okay, so an obvious sort of almost tautological thing to do is to say if a distribution is locally stationary if that Dirichlet form is small. Okay, and that's what we'll do. We'll just say that. I think I can erase this. Here's the definition 2. Both are very much related to each other. This is our correct definition. This is the definition we'll use. A measure is epsilon locally stationary if its Dirichlet form, if the Dirichlet form, which is ft log ft, where measure nu t is locally stationary, where ft is equal to nu t by pi. And that's the density function. Okay, so this is the definition. I'm just sort of, if you look at an analog of gradient descent, in gradient descent, you say that a point is a local optima if the derivative gets close to 0, right? And all I'm saying is a distribution is locally stationary if the quantity that is in the derivative is close to 0. Okay, it's not very imaginative or thing, it's just the most.
The mysterious part here is why KL divergence. Why not variation?
Okay. The question was, why did I choose KL divergence?
Yeah.
Okay, the question was, why don't I use L1? I think the point is probably that I don't know why L1 is probably not nice and differentiable everywhere. Yeah, I don't have strong convexity, so it's not differentiable. So in many places, I don't know if that's the reason, but yeah, like usually these are strong convexity and so yeah. But you know, it's not, yeah. Okay, the question was why am I using KL divergence as opposed to L2? Right? That will become clear very soon now. Okay, that's good. Yeah, this is a good reason to use KL divergence. So here's the main statement. Well, you take any Markov chain, No, this is a particular T. I mean, the index T is not doing much here. Actually, I should just erase it. Yeah, thanks. A distribution nu is locally stationary if its corresponding density has a small Dirichlet form. Okay, and what can we say about this? Well, basically, you take any Markov chain P. Okay. If you run it for capital T steps, you will hit a point where the measure is locally stationary, right? There exists a time t in 0 to capital T such that the measure nu t is, let's say pick any Markov chain on, let's just do 0, 1 to the n, is n over t locally stationary. Why is this true? Yeah. Right. Why is this true? Well, the reason this is true is basically, as I said, the KL divergence is decreasing at the rate of the Dirichlet form, right? And the KL divergence can, this is, it's basically n for on 0, 1 to the n. Right? You cannot have KL divergence more than n on 0, 1 to the n. Does this need a minimum probability? This is minimum probability, right? Yeah. Okay, so basically any distribution that you have on 0, 1 to the n, on any distribution you have on 0, 1 to the n, your KL divergence is going to be kind of less than n. So what that means is you have a quantity that's starting at n, okay? It doesn't have much room to decrease. So if you run it for t steps, okay, at some point, it's constantly decreasing. And at some point, the rate at which it's decreasing is going to be smaller than n over t. Right? And that's it. So that's basically it. It's a very trivial thing is that, well, this is the rate at which you're decreasing. You start the value at most n. If you write for capital T time, at some point during the execution, your value, right. So now what's the advantage of picking KL divergence is that the quantity that you start with is kind of nice and polynomial for us. It's n, right? So, and therefore you can do it n over t. For L2, I think you can start with quantities that are exponentially large. Exponentially large. So
Prasad, just to clarify, you also have a quantifier on capital T. Like the theorem says, any Markov chain P on 0 to the n and any capital T.
yeah, yeah. Yeah, and in fact, this is even, it's even not just there exists a time t and a typical time, right? Because you only have n and you're going to go to 0. You're going to be at least 0. So you will never, in a typical time, if you just pick a random time, the rate at which you're decreasing will be order n over t. Right? So in fact, this is not even like a special time. This is even like a typical time. So what do I mean by typical time? Basically, if you pick time at random, the gradient there would be at most 2 times n over t with probably at least a half. So it's just a small t is not, yeah. Arbitrary choice. Oh, yeah. Yeah. Yeah, this is like, I'm not saying anything about this curve, right? Maybe right at the edge, it's actually falling down, right? It's yeah, and so I think, I mean, I think we could use, if you do L2, the initial distance could be exponentially large, right? This density, this L2 distance can be exponentially large. So, I mean, but, in the sense that, um, yeah, yeah, yeah. I mean, this is like a very basic canonical statement, just like saying, in gradient descent, if I keep going, I can't keep decreasing. So there's going to be times when I'm not decreasing fast. And that's basically all that's going on here. And it's basically just that. There's nothing very deep going on. It's just a definition right now. And I said there are two definitions. Firstly, the first one, this one implies that one. Oh, a typical time. Or what I mean by a typical time is, let's say I pick a time uniformly at random in 0 to t and see the gradient. It'll be at most 2 times the value with probably at least a half. So it's like the.
Here you're assuming that the derivative is always negative.
It is negative always.
Why?
How do you prove that? Well, you can actually look at the Dirichlet form. It's always a positive quantity. Um, no, but you can just look at the. Right. No, but if you look at the Dirichlet form, what happens is this looks like fx minus fy times log fx minus log fy. Okay. And both are positive or negative at the same time. So it's always a non-negative quantity. Yeah. So it's constantly decreasing, and it is just a. Okay, good. So what? All right. So there are two definitions here for locally stationary. Can I say something about them together? Well, there's a very natural relation between the two, which is that the Dirichlet form, as I state a fact here, this is an inequality, is at least 2 times the KL divergence between P nu and nu. And this is at least 4 times the EV distance between nu and P nu. So this is an inequality. Okay. I'm not proving it, but the point is that if the Dirichlet form is bounded by epsilon, then the TV distance is bounded by square root epsilon, right? This has to be at most square root epsilon because of the square. So basically, if you have a measure which is epsilon locally stationary in this sense, it's also square root epsilon locally stationary in the more traditional sense that we like, which is that in one step, your distribution doesn't change. So this is a more reasonable sense in which. Okay, good. So now we have the basics in. So we just have a definition, and we know that every chain more or less converges to this, converges to a local stationary measure. And so how much time do we have? Okay. Okay, good. So let me state some, I'll state some very basic properties of locally stationary measures. And then I'll. Okay, good. Over here, f would just be nu by pi. Okay, good. So some basic properties. We already saw basically every Markov chain converges to local stationary things. So here's another basic property. local stationarity is preserved over short time scales. So it's preserved. So if you are in a locally stationary measure, you'll probably continue to be in a locally stationary measure for a little time. Yeah, this is because if I go k steps, and if I look at the Dirichlet form for a k step walk, this is at most order k cube times so in some sense, if you're locally stationary, in k steps, you'll still probably be locally stationary, right? If this is less than epsilon, for small enough k, this quantity will still be small. Okay, so this is a kind of, okay. So here's another property which I think is very nice. If I look at locally stationary measures, okay, they look like stationary measures, or they're approximately stationary measures in small neighborhoods. Small neighborhoods of 0, 1 to the n. Okay. What do I mean? So if you have so let's say this is 0, 1 to the n. Okay. And you have a locally stationary measure, epsilon locally stationary measure nu on it. It's a probability distribution. And I look at a point x, sample x from the measure. Okay. And then I look at a small neighborhood around the point. Let's say a d-step neighborhood around the point in 0, 1 to the n. In 0, 1 to the n, I look at a small neighborhood. Now, if I look at the measure restricted to this neighborhood, so if I look at nu conditioned on this neighborhood, this is going to be epsilon close to the stationary measure restricted to that neighborhood. Okay, so if I look at a small part of the hypercube, you have to pick a part which is sampled from, the center should be sampled from your measure, then actually it'll look like the stationary measure there, right? And I mean, another, like, yes. Yes, yeah. So actually, I should say this is some function of, the distance is some function of epsilon and d and so on, right? Yeah. Oh, the here? No, it doesn't depend on the chain. It's universal constant, yeah. Thanks, yeah. Yeah, and so, like what else is going on? I mean, another way to say this is, this d. No, the statement is you fix any d. Fix any distance d neighborhood. Okay, and you fix any d, and then you pick suppose you have a epsilon locally stationary measure nu, and then you sample a point from the measure, and you look at the distance d neighborhood. Condition on that neighborhood, just restrict to that neighborhood, your measure looks just like the stationary measure. Okay. And I guess I'm sort of being very loose with epsilon here, because as you can see, I can set epsilon to be any inverse polynomial or anything I want. You know that, if I run for t steps, I can get roughly n over t stationary measure. So think of t as like n to the 4 steps. Then epsilon will be 1 over n cube, right? It depends. I can set epsilon whatever I want, and I can reach a stationary measure with that level of stationarity. So okay, good. So here's another consequence of that statement is that so actually, what, let me state this consequence later. All right, so we've been talking about some definition of locally stationary measures and some properties of it. That's all good, but it's only interesting when you have an application of these definitions. And it's kind of the same thing with local optima and convex optimization. It's easy to define them, it's easy to get to them, but it's hard to say anything that's useful about them, right? So here, I'm going to show you two applications of local stationary measures. All right, so the first application is the following. So it's a kind of a very simple application. So the application is finding large independent sets. In triangle-free graphs. Okay, so what is it? So here's a theorem by Aitai, Komlosh, I think Semeredy. Has to be Aitai, Komlosh, Semeredy, and there are, I guess, many other proofs of it now, is that if you have a G is any degree D, maximum degree D, degree D, triangle-free graph, then there exists an independent set of size at least n, the number of vertices, times log d by d. I think the constant is 1 if you want the exact constant, but here I'll just be a little bit, I'll just say omega. Okay, so what? Correct. But why is this interesting or why is this surprising is the basic greedy algorithm in any deregular graph will give you an independent set of size n over d, right? Because you have a graph, you have every vertex is connected to d things, right? You take a vertex, you put it in the independent set, you throw out all its neighbors. The greedy algorithm finds you an independent set of size n over d. And what this is saying is that on most graphs, in fact, or in a typical low degree graph, which doesn't have any triangles, you take any graph with degree at most d, which doesn't have any triangles, it has an independent set which is much larger than what the greedy gives you. It gives you something which is n log d by a factor log d. Okay? And there are constructive versions of this theorem too. It's not, it's a fairly classic result, and there are constructive ways to find the independent set. What we show is that if I just run global dynamics, this is all of those things that I'm going to talk about today is joint work with Kuikui Liu, Mohanty, and David Wu, and Rajaraman. Yes, I got it in the wrong one. Yeah. Amit Rajaraman. He's a student in MIT, quick student in MIT, and myself, and David, who's also a grad student. So what do we show? We show that if you run this global dynamics for the number of steps doesn't matter, but I guess you can, if you want, number of steps, what I mean by number of steps doesn't matter is in our worldview of things today, we're just going to run the chain for polynomially many steps, n to the 5 steps, and you're going to get a locally stationary measure, which is 1 over n to the 4 locally stationary, right? So this returns an independent set of size, whatever, the omega log d by d times n. So what is happening is, if you look at the global dynamics for independent sets that we saw here, this chain doesn't mix, or in most graphs it doesn't mix. In fact, for it to mix, you have to work with a much higher yeah, it's you have to work with a much higher temperature, right? This is, yeah. So this chain doesn't mix, right? So, but what we are saying is, well, it doesn't mix, but if you run it for n to the 5 steps and just extracted the whatever measure it gives you, that measure has, large independent sets with very good probability. Okay. Run global dynamics. Start with some set, maybe even the empty set. Or you can run with start with the empty set, and you run it for some that long, and you look at the set that you have, and the size of the set, the size of the independent set the expected size of the independent set is going to be at least log d by d. Yeah, yeah, exactly. There's no, because it's just the chain always has walking on independent sets, right? So at all points in time, it has an independent set. All we're saying is, the size of the independent set will be n log d by d. Oh, what's temperature? Yeah, maybe I will, when I talk about icing models, I will come to it. But here I don't need to as of now, but I'll keep that in mind. When I come to icing models, I will talk about temperature. Thanks. Yeah. Any other questions? All right. So how is it compared to a maximum independent set? So there are graphs where this is tight, right? So you couldn't do better than that, right? Yeah.
Well, maybe the question was, can you care about the concept?
Oh, right. The question is, can you get the right constants? Yes, that's a great question. I'll return back to that. Yeah. Okay, good. So let me say how the proof of this goes, right? So the proof. Okay, I think I can erase this, right? Yeah. So how do we prove this? Well, the idea is the following. So let's just look at uniform distribution or independent sets. Okay, that's the stationary measure, right? And you can prove that if I sample an independent set, I, from uniform distribution or independent sets, then the size of the independent set is omega log d by d times n. Okay? This you can prove. There's a proof of this. I'll show you some of the proof. There's a proof of this. I guess it's by Alon Spencer, I think. There's a proof of this statement. It's just a statement that if you pick a uniformly random independent set, then actually its size is at least this much. Okay, and what we will do is, we will just say that the same proof also works if you replace the uniformly random independent set by, if pi is replaced by a locally stationary, pi is a locally stationary measure. For so the idea is that the proof uses so little about the uniform distribution of independent sets, which you can't sample from, that the same proof can also work, also holds when you use a locally stationary measure. And while that just completes the proof, right? Because it just says that if I replace this, well, yeah. Okay, so how does the proof of this work? Let me show you how the proof of this looks like for uniformly random independent sets. Okay, for pi. All right, so yeah, uh, that's right. That's right. Yeah, but yeah, that's right. That's right. But you know, you could, yeah. Okay, so let's see how the proof of this goes. I'm going to prove this claim. Okay, and to do that, let me just define a local function. Here's a local function of an independent set. P of x, P sub v of x. So let v be a vertex of the graph. Okay, and P sub v of x. So P sub v of x is d times x sub v plus sum over all the neighbors of vertex v, x sub u, where x is an independent set. Okay, if I give you an independent set, phi sub v of x is a function, which is basically d times the vertex v's value v and plus the sum of the neighbors. Okay, so your vertex v, then okay, so oh, what is x sub v? So x is an independent set. So phi sub v, sorry, phi sub v is a function from independent sets to reals given any independent set. It's an independent set is given by a Boolean string, which tells you whether every vertex is in the independent set or not. So actually, another way to write this is phi sub v of an independent set I is d times indicator that the vertex v is in the independent set plus sum over all the neighbors of the indicator that the vertex u is in the independent set. Okay. It's just a function of the independent set. Okay, and so basically you get d points if you put vertex v in the independent set. If you don't put vertex v in the independent set, you get as many points as you put, as many neighbors as you. It's just a scoring mechanism, right? So you know what is nice about this? If I sum up these scores over all vertices of the graph, okay. Well, basically every vertex gets a d from phi sub v and gets a 1 from every neighbor. So this is, you get that this is at most 2d times summation x sub u. If I sum up the scores of every vertex, I get something like this. This is just by adding up this over all the vertices of the graph, right? I get a d, a coefficient of d when for x sub v, I get a coefficient of d from phi sub v, And from every phi sub u, I get a coefficient of 1 from all the neighbors. So what is this? This is 2D times the size of the independent set. Right? So in some sense, if I want to lower bound the size of the independent set, the size of the independent set, which is summation x sub u v, is at least 1 over 2D times these local scores. Okay, so this is, if I lower bound the expected value of this, I get a lower bound of the independent set size. Yeah. So I'm just, right now, we're not even talking about locally stationary measures. We're just picking uniformly random independent set, and then we're trying to understand the size. Okay, good. So now let's look at this quantity. The expectation of P sub v of x when x is a uniformly random independent set. Okay, if x is uniformly random independent set, so I have colors here, yeah. Okay, so let's say there are, k vertices that are not blocked by vertices at the two-step neighborhood. So let's look at, let's freeze everything outside the neighborhood and ask what's the expectation of phi of u. Okay, so if I freeze everything, all the independent set vertices, okay, outside the neighborhood. So let's say these vertices are all fixed to be part of the independent set and so on. Now I'll just understand what's happening inside the neighborhood. Okay. Okay. Inside the neighborhood, some vertices cannot be part of the independent set, right? Some vertices can still be part because this vertex doesn't have its neighbors picked, so it can be part of the independent set, and this vertex cannot be. So if I look at this, suppose S is the set of vertices of the set of neighbors of the graph of the vertex V, such that a vertex V in S, U in S can be part of the independent set. Condition on everything outside being frozen. Okay. So we're not assuming that. We're not assuming that. I'm just going to compute this quantity. I'm going to freeze everything outside the neighborhood. I'm going to compute this quantity. And to do that, let's S be the set of vertices of the neighbors that can be part of the independent set, that, given the outside is frozen. Well, here I'm freezing only the vertices outside. I'm freezing everything here. I haven't frozen anything inside the graph. So everything here is an option. I could do 0 or 1 here. And S is a set of vertices which I could include. V also I could include, right? All right, so now if I look at a uniformly random independent set, I'm going to pick a uniformly random configuration here, right? A uniformly random configuration here. There are 2 to the S configurations where I pick a subset of these guys and I don't pick V. There's only one configuration where I pick V and I don't pick any of them. So this is at least 2 to the S by 2 to the s plus 1 times s over 2 plus um, um, if I pick vertex V, then I don't get to pick any of its neighbors. So my score will be D, right? D times with the remaining probability. Okay, I'm sorry, I'm making a mess of this proof, but I'll fix the mess by sort of stepping back. If you didn't follow this part of the proof, completely ignore it. Just follow, the message I want to say is the following claim is true. The claim I want to prove is for every conditioning of the remaining vertices, for all conditioning of the remaining vertices, the expectation of phi of xv conditioned on the remaining vertices is at least log d by d. Okay, that's all I want to say. Right, you can look at this expression and minimize it for the choice of s. You'll get log d by d. The claim is just that. Forget about everything, all of these details of this argument. The point is just that under the uniform distribution over independent sets, if I look at a vertex and I look at its neighbors, if I fix everything outside the neighborhood of x, right? This is the neighborhood of x, neighborhood of vertex v. If I fix everything outside the neighborhood, however I want, and I compute the expected value under the uniform distribution, I get this local score function is at least log d by d. Yes. Sorry. Oh, I'm not even fixing v. Yeah, not fixing v. It's just outside the neighborhood. Sorry, everything outside the neighborhood is fixed. Oh, this one. Basically because, okay, at this point, what you have is a tree. Locally, you just have a tree because it's triangle free, okay? And you have a vertex V here, and then there are S vertices here, which you could potentially include. Now, when you look at a random independent set here, what can you do? You can decide not to pick V, okay? Then there are 2 to the S choices for the independent set here. Or if you decide to pick V, all these have to be empty. So there's only one choice where you pick V and then you get a score of D. In every other choice, you pick some subset, random subset of the S. So you get a average score of S over 2, and you get that. So, but basically, the point is that there is a very simple proof that relies on just this local neighborhood structure of the graph of the vertex V that shows that no matter what you fix outside, the expectation of this local function is at least log d by d. No, S is basically the set of all things that can be in the independent set, right? S is basically what we have done is we have frozen everything outside. Once you freeze everything outside, some of these vertices are precluded from an independent set, some are still allowed, and S is the set of vertices that are still allowed. I think no, I think AK's got a half. I think this is also getting a half, but I think Shearer improved this to 1, and I think even for 1, it's not. There are no algorithms known for that. Yeah, it's not even it's not even right. Exactly, it's just not even an algorithm, right? It's just saying that if I pick a uniform random independent set, its size is this much. Yes, this can be made algorithm. The reason, yeah, Right. So okay. Okay, so this is all good. This is still a proof about a uniformly random independent set. Okay, and the main claim is that your proof, what did it do? For every fixing of things outside, you studied the uniform distribution of independent set here, right? So that's by the, so by the, and you computed its expected value, and you said it's at least log d by d. Okay, it's a function just of the neighborhood. It's just a function of this neighborhood, and you're saying that its expected value is at least log d by d. Okay, and we said that if you look at a locally stationary measure, in any local neighborhood, it looks arbitrarily close, epsilon close to the uniform measure, right? So so this expected value will still be the same. This will be the same even under locally stationary measure. So even under locally stationary measure, this expected value will be at least log d by d. Like it'll be the same as, it's not, I mean, in fact, these two quantities will be the same. This expectation is going to be the same. For every locally epsilon locally stationary measure with some epsilon error, this will be the same. Okay. Right. Yes, because in some sense these bits are all fixed, right? And we're only changing d+1 bits. These d+1 bits we are changing as we want, right? And so we're only moving in the neighborhood of the vertex in the on the hypercube. We're also allowed to change, but I'm saying this proof, I just look at this proof. This proof, the same proof also applies to any locally stationary measure. You take any locally stationary measure, the same proof will apply, this thing that we did here, because these probabilities will be the same to this, but everything will be the same. Like it'll just look like uniformly. Correct, correct. Yeah, it's because a neighborhood in the graph, right? This is basically, I fixed everything outside this neighborhood. So it's the set of all independents. Once everything is fixed, there are only d+1 vertices here. And so it's only, you're looking at all independent sets with, which are within distance d to one independent set. So the measure restricted to that will look exactly like uniform measure. Up to which independent set? Let's just say x sub nv and 0 everywhere here. Yeah. Yes. Right. Right. Yeah. Yeah. But it doesn't matter. Yeah. 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 I guess there was another statement which I did not state. I guess I skipped over, is that here I'm talking about locally stationary measures look like stationary measures in small neighborhoods of the hypercube. If you have like a bounded degree setting or something, you can also talk about, it looks like stationary measure on local neighborhoods of your graph in a sense, which is kind of what I'm referring to. But they're all very similar, related to each other. Yes, yes, exactly. Yeah, yeah. Right. So this is just a translation. So, but we got this log d by d here. And therefore, the whole proof goes and you get an independent set, right, set of size log d by d.
Small number of for example, if you graph average degree.
The statement is still true. I think this statement is still true if the average degree is log d by d. Average degree is d.
Shear arbitrary triangle free graph of average degree d, the same output.
Yes, Shearer proved that.
But that proof doesn't work with.
Probably. Yeah, yeah, probably we need to make it work. I'm not sure actually. Yeah, yeah. We just, yeah. Okay. Yes. Where's the triangle freeness come in? So here, when I said that, Once you fix everything, I'm just have a little tree here, and I wrote down these probabilities. These probabilities are based on the fact that this neighborhood is a tree, just a star graph, right? It wouldn't, and otherwise I wouldn't get two to the s independent. The point is, I said if there are s vertices here which are allowed, there are 2 to the s, all subsets of it are allowed. That's only true because there are no edges among those neighbors. Yes, yes, yeah. Correct. No, I mean, there are, I mean, just if you go into this graph theoretic statement, there are much stronger generalizations of this where you say some triangles are allowed and some for example, if I'm saying triangle free, I could have said cake leak free. And then there's some proof statements. All of them get you log d by d, and there's lots of. I'm not sure actually how all the proofs go. In fact, there's a fairly involved versions of this state theorem. Okay, so I think I only have 8 minutes. Okay, so, oh, I have 15 minutes, great, okay. Good. Yes. Yeah. Oh, so given this expected value is at least log d by d, right? Sorry, I should be more clear here. So what this means is that the size of the independent set is at least 1 over 2d times this. So if we take expected value, I get this is n times log d by d. Yeah. It's true for every conditioning. So the expected value is also at least log. Yeah. Sorry, I think I made a mistake here. This should be log d, not log d by d. You get the 1 over d from here. Yeah. I'm sorry, but yeah, completely. Yeah. Okay. I should just follow my notes. Okay, so what will I do next? I will, this was just a warm up to show that you can actually use Markov chains even before they mix, right? In this case, to find independent set. You can also use it to find max cuts with 1 over square root d advantage and so on. But let me actually state what we're going to do next. So the thing that I want to state next is recovery in stochastic block models. Stochastic block models. So what is this? Let me define what a stochastic block model is. SBM, right? This is basically a random graph model. So how do you sample a random graph here? So it has 2 parameters. Let me say SBM of n d n lambda. So I'm going to do 2 community stochastic block model. So what you do is you first take your n vertices and group them into 2 sets. Let me call this S complement, independently at random. So meaning you sample X from plus minus 1 to the n, 0, 1 to the n, plus minus 1 to the n, which is basically uniformly at random. And that tells you whether the vertex I is on the left or on the right. Right? X sub I tells you whether the vertex I belongs to the left or the right. Okay, these are your hidden communities. There are 2 communities in your graph, right? Let's say like in the context of United States, it'd be like Republicans and Democrats. There are 2 kinds of community. There are 2 communities here, right? And then your graph depends on is a random graph which is chosen based on the communities. So, right, if you look at any edge ij, here's where we sample the edges. Okay, an edge ij belongs to the graph with probability. Well, basically it belongs to the graph with probability d over n, right? D over n, if I sample every edge with probability d over n, I get a uniformly random, Erdős-Srény random graph. But here, it belongs to a graph with slightly higher probability if they belong to the same community. D plus lambda root d by n, if xi is equal to xj. And if they belong to different communities, then there is an edge with a slightly lower probability. Okay, so you're drawing edges uniformly at random. Each edge independently, if they belong to the same side, if ij on the same side of this partition, then you add edge with probability something slightly more than d over n. Okay, if they're on the opposite sides, then you add with probability something slightly less than d over n. Okay, so this gives you a graph, a random graph. So this stochastic block model is a joint distribution between x and g, right? It's a joint distribution over x, which is basically uniformly random, and g. And what is the canonical problem here? The canonical problem is I give you the graph and ask you to find the communities, right? So the recovery problem is given g, recover x. Let me call it x hat because that's our x hat is our original choice of communities. Okay, given g, recover x hat. This is basically the stochastic block model question and recovery problem. And of course, what's the most correct thing to do is to do the Bayes optimal thing. The Bayes optimal thing is to do sample x conditioned on g, right? We see the graph g. We know the joint distribution between x and g. So we just sample from that distribution. That'll be the best thing to do if we could sample, right? But we don't have good sampling algorithms for this yet. Okay, so now we look at this distribution. Let pi be this distribution of x given g. Pi be the distribution of x given g. Okay, it's a probability distribution over 0, 1 to the n. Sorry, or plus minus 1 to the n. You can write it out. We can just write down and apply Bayes rule on this probability distribution. I can write it out. And basically, you're going to get an expression which says pi of a point x is proportional to some beta times summation gij xi xj. Where gij is the graph. Gij is adjacency matrix of the graph. It's 1 if ij is 1. Or let me just sum this over edges. Sum over ij in the edges of the graph, xi xj. Okay, you'll get a probability distribution which is proportional to e to the power summation xi xj, where ij is the edges of the graph. Okay, and this is some probability distribution, and if you can sample x from this probability distribution, we'd be done. Right? In fact, that's the best we can do for this problem. Okay. So what do we know about this thing, this problem? Well, we know that if you start with, if you look at the parameters here, there are two parameters, d, which is of course the degree of the graph, okay? And lambda is, if you want to say, use the word, it's like the signal strength. Lambda is like the signal strength. Why do I call it that? Basically because lambda determines how much different the edges across are from edges within. Right? You see that the difference between edges are going across the two communities to edges within the communities is basically parameterized by lambda times square root d by n. Right? That's the key difference. So as you increase lambda, you're increasing the chance of edges inside and decreasing the probability of picking edges across, and vice versa. So therefore, lambda is like the signal strength. For sufficiently small lambda, you should not be able to recover x. And in fact, that's what is known. This is by Mosul, Neiman, and Sly. Right, for lambda less than 1, less than or equal to 1, I guess, it's information theoretically impossible to recover. It's information theoretically impossible, meaning even if you did the Bayes optimal recovery, you'd only get, you won't be able to recover x hat well. So basically, the way to see how well you recovered x hat is to measure the correlation. X hat is a true communities that was planted, and x is what is recovered. Right? This will be Litlow of n. Okay. Or if I look at what, let me just. So what is this? This is the. So let's just look at 1 over n times this. Okay. If I look at this quantity, 1 over n times. If I look at this quantity, 1 over n times. This is basically on average. How well do I guess the community label of a vertex? How well do I guess the community label of a vertex on average? Right? If I guess the community label right, I get 1. If I guess the community label wrong, I get -1. This is on average. And the point is, this is going to be Litlow of 1, meaning I don't have any advantage over random guessing if the signal strength is too small. Okay?
For random, you would have expected 1 over root n. Should I be splitting hairs between Litlow of 1
I don't know if we know it well enough to give 1 over root n bar. Right?
What do they expect?
I'm not sure. I had to think about it. Yeah, I'm not sure. Yeah. So, okay. So, but basically, if the signal strength is too small, you can't do anything. All right. You can't recover the communities. Okay. Let's just focus on when signal strength is large enough. Right. So again, Mosul, Neiman and Sly, and there's Bordenau and others. For lambda is bigger than 1, there are efficient algorithms to recover some x. Right. There exists efficient algorithms to recover some x such that the average correlation x hat 1 over n times this is some constant, meaning you're doing at least a constant better than random guessing. Like let's say you're guessing the community label of every vertex with probably 0.6 or 0.7 or something like that instead of 0.5. Okay. So this is true, and this efficient algorithm is based on the spectral method. You run eigenvalue computation on the non-backtracking walk matrix of the graph, and you can basically eigenvalue computations can be used to find the community, which is a classic community detection algorithm to run. Basically, given the random graph, compute its second eigenvector that should tell you information about the communities. Okay, so what's the question now? The question is, if you just run Glauber dynamics, can you recover the same? If you just run Glauber dynamics on this graph, does it recover the communities with the same bound, right? And in fact, we prove that that's true, that if you run Glauber dynamics on this measure, right, you run Glauber dynamics for n to the 4 steps, then you just you'll reach a locally stationary measure, and that locally stationary measure will have a correlation which is omega 1. Yeah, well, okay, thanks. For sufficiently large lambda. For sufficiently large lambda, running for sufficiently large constant lambda, I have it written down here, but I'm just stating the gist right now. For sufficiently large constant lambda, the Glauber dynamics after n to the 4 steps reaches a locally stationary measure, and that locally stationary measure will have a good correlation with the true community. Okay, and if you step back and say what is going on, what's going on is we are effectively proving that this distributed algorithm, which is kind of the Glauber dynamics, a very distributed local algorithm, actually can do eigenvalue computations in a sense. Right? It's not eigenvector, can run the spectral method, can compute the eigenvector in a sense. We're not proving that you can compute the eigenvector, we're proving that it has correlation with the hidden communities, but that's what it is. It's saying that Glauber dynamics can simulate spectral method in a sense. And kind of it's kind of nice because this is actually, if you don't have eigenvector computations, this problem is very hard. For example, you can run linear programs of any hierarchy up to sub-exponential size linear programs. You will not recover the cut, right? This is LP lower bounds for max cut. LP lower bounds for max cut and so on. What do they say? The graphs are random graphs, and they say that even if you have sub-exponential sizes, Lower Shriver, SD, LP linear programs, they can't recover the cut. Basically because linear programs completely are unable to just do the basic spectral eigenvalue computation. But Glauber dynamics kind of does it, right? It's able to do it, so that's why. Oh yes, that's another point. If the Glauber dynamics had mixed, if you run it for exponential time, you would get the Bayes optimal solution. So in that sense, it's not surprising. But the things that, but in n to the 4 steps, already it's giving you something which is fairly good.
Do you expect the same algorithm to actually work?
Yeah, I would expect that it should give you for any lambda bigger than 1. Thanks. Yeah. So in the second part of the lecture, I'll go into the proof of that fact. Or SPMs.